Andrews, Scotland. I'm a third-year PhD student co-supervised by Dr. Tristan Henderson and Dr. Juan Ye. Today I'm going to talk about our user study about location privacy recommenders. Nowadays everyone has a smartphone which has GPS and 3G, 4G on it. So thanks to that, we can share our whereabouts to everyone in everywhere. So for example, we can post a picture on Facebook and tag where we took that picture, or we can just check in a restaurant on Foursquare, or we can just share our live trajectories with each other on the Glimpse. And these location sharing services provide fun and convenience to our lives. At the same time, it is very important to protect our location privacy. The first reason is, according to existing research, among all the data in people's mobile devices, they value their location trajectory the most. And secondly, some of the locations could be sensitive. For example, if I visited a clinic or hit in a pub or go to a long distance travel in the airport, I may not want everyone to know where I am. So, well, let's have a look at how we can protect our location privacy on Facebook. So here's an example. I am, drinking in a pub with my friends. So how many steps does it take to preserve my location privacy before I share it? So first, I need to click on the drop-down list friends, and then if I want some customized preferences, I need to click on more options, and then click the custom. So finally, I got the interface which I can configure to which groups I want to share with, to which groups I want to hide from. So you see, every time, if I want to share my location, I have to do this tedious work manually, which means we need something easier to be used to protect our location privacy. So what have we done? There's a lot of work has been proposed to use recommender system or machine learning classifiers to protect our location privacy. For example, we can use neighborhood-based crowdsourcing data to predict and automatically configure our location privacy settings. Or we can just use our personal data and use model-based classifiers to predict our preferences. Both of these methods, they have very good objective performance, which is a prediction accuracy. So which means these recommenders have the potential to be used in the real world to do this tedious work for us. But there's still a gap to understand how the users in the real world accept such recommender systems, because existing works mainly focuses on how accurate the recommender is. Most of them, they didn't consider the user's acceptance. So here comes to our research question. Would people accept such recommenders in the real world? So the user's acceptance is the metric we care about to investigate in our research. So generally, their acceptance will be influenced by two groups of factors. So you can see on the left side, there are the subjective factors from the user. For example, a user may trust a technology very much. So the user may trust, okay, we can use the recommender to do it for us. Or maybe some other users, they have concerns about providing the data to the recommender system, so they may be reluctant to use it. So this is from the user side. And the other group is from the recommender itself, which is objective factors. For example, in terms of crowdsourcing recommendations, would the source of the crowdsourcing influence people's acceptance? Such as, would they trust their friends more than the similar acquaintance? Or would they have different acceptance in different time and location categories? So here is the general framework we are going to investigate what subjective factors and what objective factors influence people's acceptance of our location privacy recommenders. So to do that, we designed our online experiment platform. The first part of our online user study is the pre-briefing. So we advertised our platform through the university mail lists and also through the university Facebook groups. And we had 99 participants to finish our experiment. So in the first part, we claim we have developed 3 types of crowdsourcing recommender systems to provide location privacy recommendations. The first one is using the people at the same place as the crowdsourcing source. The second one is using people who have similar location privacy preferences. And the third one is using their Facebook friends' opinions. So we also use some examples to familiarize them how these recommenders work. So this is the first part of our online user study. And after that, we asked the participants to log in with their Facebook accounts so we can access their location checking histories. Then now comes to the second part of our experiment. Here is the interface we provide recommendations to them. On the left side, there is a map generated from the coordinates of their check-in. And on the right side, there is the context of their previous check-in. And here is the recommendation from one of our recommenders. Because we want to investigate whether the source of crowdsourcing influenced their acceptance, so we need to keep the accuracy the same. So to do that, in fact, we used the same random generator for all these recommendations, but the participants were hidden from this fact. So they thought we really designed 3 different recommenders using different crowdsourcing sources. And at the bottom of this page, the user could select whether they accept or not. So after going through this recommendation 30 times, it will be the final part of the online user study. You see on the left side here is the summarize of all the users' choices for one of the recommenders. And on the right side, for example, in this page, this is a questionnaire to evaluate their perceived quality of our recommendations. And this questionnaire contains 7 questions. Each one is a statement which could be answered by option in the 5-point scale from strongly disagree to strongly agree. So this is the final part to evaluate their subjective factors. So coming back to the framework we mentioned above, for the evaluation, we evaluate their trust of technology, their perceived quality of the recommendation, their satisfaction about their choices, and their privacy concerns about using our recommender system as the subjective factors in our experiment. And we draw on the questionnaires from this paper to design our own questionnaires. So this is the subjective part of our evaluation. And for the objective part, we evaluate the source of crowdsourcing and the time and location of the recommendation, which is the context, and also the openness of the recommendation. So because the left side was evaluated by questionnaire, we did some pre-processing to testify the validation of their answers. For the trust of technology, it didn't pass the confirmatory factor analysis, so we just removed it from the further analysis. On the right side, we didn't find any statistically significant difference from the source of crowdsourcing. So which means our participants, thank you very much, they just treat the recommendation as the recommendation from others. So the first effect we found is from the privacy concerns. So you see, each square is a subjective factor, and here is the acceptance evaluated from their interaction. It's the percentage of the accepted recommendations. The red number means is a negative effect, and the blue number means is a positive effect. So you see, from the concern, there's a negative effect to the quality, and from the quality, there's a positive effect to the acceptance. So there's an indirect negative effect from concern to the acceptance. So the more concerns they have, the less acceptable the recommendations they think. So we need to adjust their privacy concerns about using our recommenders. And the second effect we found was from the openness. We used the default privacy settings from Facebook, which is sharing only to myself, to friends, friends of friends, and everyone else, everyone on Facebook. So the least open one, which is only me, and the most open one, which is everyone, both of them have the least acceptance. So we were very interested why this bar is very low, because we thought this one protect your privacy 100%. Why won't you just accept it? And then here is one instance from the text comments from of our participants. The participant said, if I would just share something to only me, then why would I share it at all? So it looks like our participants, they won't just give up their social benefit for the trade-off for the privacy. And also for this one, two of the participants, they said they need the threshold to control how open the recommender could be. Thank you. So which means the designer of our recommender should be very careful about the openness of the location privacy processes. And the last effect is from the context. Here is the 5 time slots from morning to night. And we aggregated all the check-ins into 4 location categories. You see, for all these 5 time slots, the school, university, library category always has the highest acceptance. And most of our participants, they are university students, which means this is the most regular context for them. So, and here is the feedback. I think, so the participants said the regularity should be considered by the recommender system. And also, for the least accepted one, which is the transport, the participants said, well, if I share my location in the airport, then someone may know I will be away for a long time, so someone may break in and steal my things. So it looks like they took into account the potential risks caused by the unsuccessful recommendations. So we speculate the regularity of contacts and the potential risks of unsuccessful recommendation would also influence their acceptance. So summarizing our research, first of all, we need to consider privacy of our recommender system. And also, we need to be very cautious about the openness of the recommendations. And finally, the context always matters. So for the future work, motivated by our first finding, if the participants, they don't trust a centralized server, why don't we just get it off? If we can cooperate in a decentralized, self-organized way, then why not? So, yeah, so that's all. Thank you.
Thank you very much. We have time for questions. Any questions? While you think about your privacy questions, I will ask one. So I was wondering, the participants, they basically, there was no hint towards the consequences of the privacy recommendations, to the positive or negative consequences. This was something that the participants had to basically make up on their own, I guess, yeah? Or did you explicitly tell them, oh, you other, in this situation, you mentioned the airport situation, but this was something that the participants had to come from themselves, yeah? So I was wondering, what would you think if you would provide such kind of consequence-based hints towards the participants?
Well, actually, when we advertised our experiment, we avoided to use the keywords like privacy or things like that, because we felt if we did that, then it might bias the sample, because some privacy fundamentalists, they may more likely to take, oh, this is the user study about privacy, then I will take part in it. And they may be very careful about their privacy. So what we use the keyword is the location sharing decision. So we don't use location privacy, because we don't want to scare them, then it would influence the effect we found in it.
Okay, okay, I'll see.
Hi, so Ossie from Haifa University. And my question is, what were their normal sharing behaviors? Were they consistent with the way they're normally shared, or did they use your recommendation the way they normally would share, or would they change it because of your recommendation?
Well, that's a good question, because we were planning to get what they really did, what their actual location privacy process was. But we used the Facebook API, but we didn't get the data from the JSON response. So yeah, that's a really good point, because if we have the ground truth, whether they share at the first place or not, then we can evaluate if our recommender changed their behaviors. But we could not do that because we didn't have the data.
Yeah, my experience is that people who share publicly would also share publicly their travel plans and stuff like that. They would not suddenly make it more private, but this would be an interesting.
Yeah, that would be interesting to investigate if we can find a way to just grab the data from them.
Right, thank you.
Thank you.
Okay. If there are no further questions, let's thank you once again.
Okay, thank you.
And we come to our next presentation. That's the second talk, another long paper, is on data portraits and intermediary topics, encouraging exploration of politically diverse profiles. I guess we will see maybe some more pictures of Trump. I don't know. That might be appearance number 3 and 4. Yeah, 5. No Trump pictures.
No Trump pictures.
No Trump pictures. Very good. And the presentation will be given by Eduardo Grels Garrido. Please, Eduardo.
Thank you for the introduction. Good afternoon, everyone. Thank you for being here.
Could you use the VGA out?
It's BGA.
It's VGA. Okay. Thank you.
Okay, so this talk is about data portraits. What is a portrait? I hope that you recognize the portrait that it's on the screen. Who doesn't recognize this portrait? Oh, okay. So you should recognize it. It's a portrait of Ada Lovelace, the first programmer. Okay, so what is a portrait? A portrait is more than a picture, and it's more than a painting. A portrait is an artwork that is supposed to capture the essence of someone, and that is what this talk is about. What is the motivation behind this talk? Is that on Twitter you have this cognitive bias that affects how people interact with others, that is called homophily. So homophily means that you connect with others, you interact with others who are like-minded, who think like you. So for instance, this is a discussion network on Chile about abortion. You see people from people with the purple color are pro-choice, and people with the green color are pro-life. You see that people from the same color tend to be connected with others, and even you see small clusters of only one color. So the idea behind this talk is to see what can we do about that, if we can encourage people to connect with others who think differently. Particularly the research questions we have is it possible to encourage exploration and acceptance of user profiles recommended on the basis of political diversity? If so, which factors influence this behavior? If you look at the literature, there are many approaches to try to solve this problem. So for instance, the first one, the most obvious one could be also, it's filtering data. So you have a list of recommendations, and you try to create a diverse set of recommendations, very similar to what we did yesterday with locations, right? But also, if you have a list of recommendations that could be diverse, you could try different presentation techniques, like clustering, sorting, highlighting. Also, others have used directly, instead of changing the presentation, is completely changing the paradigm and using visualization to show the recommendations. And finally, you can give user control of what he is seeing or she is seeing on the screen. Maybe you can say, I want to see people who think differently. In all these cases, the approach hasn't worked very well. Some things have happened. For instance, when you use visualization, people behave differently. Not less biased, but differently, more respectful, for instance. So why does this happen? Yesterday, someone asked, do people want diversity? And actually, people, I don't know if they don't want it, but they do not value diversity. If you look at what all these other approaches have in common, is that they are direct approaches. So they want to change how you behave. And that doesn't work, because it's like pointing to you what is wrong with you. And biased behavior exists because it is easier cognitively and socially to be biased. So what is our approach? We want to create an indirect approach, first by taking advantage of homophily to create positive first impressions. So we want to recommend you someone who will create a good first impression for you. First impression matters. It depends. The first thing you see about someone will determine what how do you react with following interactions. How do we do this? Using intermediary topics, which is topics detected with latent direct allocation with some properties that we will see later. And we will display those recommendations in a context that emphasizes your self-image, this portrait. So you see that this portrait is about you, and you see these recommendations of people who you may have a good first impression. So what are intermediary topics? If you have a corpus of Twitter users, you can estimate LDA on this corpus. You can build a topic graph where each topic is a node, and two nodes are connected if both topics contribute at least to one person, to one account. So you can give weight to these edges based on the number of people that they contain, and you can estimate some weighted notion of centrality. We tested with weighted information centrality, and we defined that the topics that have centrality above the median of centrality are defined as intermediary topics. And in the workshop paper, we found that these topics have significantly more political diversity in their users than non-intermediary topics. And what are the portraits? Because the initial portrait was an example, and it contained something recognizable. You see, you know that what you're seeing is a person. But in the case of data, you see user-generated content. You see content about someone. Well, Judith Donat, who is a researcher at MIT, coined this term data portrait to see this is the portrait of yourself based on your data or in data about you. And they have a project that is called Personas, that takes the information that is written about you on the web and categorizes according to several topics, and they can create this visualization of you. The idea is that if you create a visualization of someone else that could be Donald Trump, but it isn't in this case, you can compare what are the topics that they care about. So, knowing this background, let's talk about our platform. So the idea is to present a data portrait of a Twitter user. We generate recommendations using intermediary topics, and we display this on the screen, and we try people to explore their content, but also follow or explore recommendations. The recommendation algorithms is detailed on the paper, but it's very simple. It can be summarized as a balance using an F score between similarity, estimated using a Kullback-Leibler distance, between the topical distributions, estimated using LDA. And since you have those topics, you can see which topics that has every user are intermediary and estimate the Jaccard similarity between the target user and the recommended candidates. So you balance both factors, and you have, for instance, on one hand, you have people who talks like you because they have high similarity, but others who may have a lower similarity, but a high Jaccard similarity with intermediate topics. So this is the design of the portrait that we have. This is a friend who allowed me to use his portrait on the screen. And these are the topics that he talks about. It's different topics, different hashtags, different mentions. There is a color for hashtags, a color for mentions, a color for other words. You see, this is a word cloud, but the word cloud is linked with a time histogram. So you can find when did you talk about specific topics, and what is the most representative topic tweet about that topic at a specific time. Also, if you look at the smaller pictures, you see that you can pick one bar of the histogram and you see what have you talked about in that time. Or if you pick a concept, you see when did you talk about that concept. So you can play a lot with this data portrait with the idea of reinforcing the image that you project on Twitter. And what is the trick? Is that just below this visualization, we display the recommendations that try to be politically diverse. So these recommendations are generated using the algorithm described before, and they are displayed using visualization. Why visualization? Because, as I mentioned, visualization could change the way that users behave, but that is not tested, and this is it's what we're going to test. Here, we use a cluster representation that is called circle packing. The clusters are defined using a very simple metric. What are the common latent topics that they have? Not intermediate topics, just the LDA topics. And the size of the avatar is proportional to the similarity estimated using Kullback Leibler distance. So we implemented this on a system that is running, and we wanted to measure three things. First, how much people explore the recommendations. Not the data portrait, just the recommendations. How much clicks they make to see the profile of someone who was recommended, and so on. How much time do they spend on the site to see if they were engaged with the site, if they use the platform, and also if they accept at least one recommendation. So this evaluation is called in the wild because it's in the jungle. We have this social bot that publishes timelines that I showed you yesterday. So we said we can use that platform to spread the word about our data portraits. So what we did was to create a tweet like the one that you see on the screen that says, explore your profile in a new visual and playful way with just a couple of clicks. So we paid Twitter for promoted tweets for people in Chile. And at the end, we got some users doing this using the systems. But before telling you how much users we had, the idea was that when a user connected their accounts with the platform, they get assigned different conditions. So first, they get assigned a random algorithm. They could use the intermediary topics-based one, or a baseline based only on the similarity between topical distributions. Also, in terms of the user interface of recommendations, they can get a text-based baseline, which is a list of recommendations in a typical way, which is very similar to how Twitter displays recommendations. But also, since we know that individual differences are important, we measured if users had political content on their profiles. So the idea is to determine if you are politically involved in discussion on Twitter, and this is so important that it appears on your profile, on your data portrait, maybe that makes a difference. And also, there are some social and interactional features like number of followers, how much retweets you make, and so on, but those details are on the paper. Okay, so our experimental setup was between subjects. On the interaction data, we ran negative binomial logistic regressions on the data. We had 129 users. You can see that the distributions of users and conditions was very good. It's not perfect because of randomization, and some users had valid, non-valid interaction data. For instance, some users left the browser open for 4 days, and no one is 4 days looking at the interface, so we had to discard those users. Political content was present mostly, almost in half of the sample, and we had 1,700 interaction events. So the paper contains a discussion about all the factors that we found that were significant and why they were not significant, and what is the explanation, but I will mention the main effects, the most important results that we found. So the first one is that Using the intermediate topics, decrease exploration and likelihood of acceptance. So that means that homophily prevails, right? So people still prefer the homophilic algorithm. Fail. Then also circle back increases exploration. That means that people made more clicks on the recommendations but did not follow them. This could be explained because of a novelty effect. So they see this new interface and they want to play with it. But also having political content in your profile increases a likelihood of acceptance. So those results are very interesting, but they are not very related to our research question. In fact, they might mean that we failed with our proposal. However, there is a very interesting result that is an statistical interaction that says when you have intermediate topics and circle packing and political content in your profile, then you spend much more time on the site than the other users. Intermediate topics reduce the likelihood of acceptance, but having political content increases the likelihood. So this is a very complex interaction. But after some careful reflection about that, and a discussion that you will find on the paper, our conclusion is that users use that extra time to decide by themselves if they accept the recommendation or not. So what does this mean? This means that they make a conscious decision about accepting recommendations or not, and this implies that maybe we shouldn't try to make recommendations more accepted, but that the user makes this decision in a conscious way and non-unconscious. That will be unbiased behavior. So, what are the conclusions of this experiment? The first one is that indirect approaches have potential. We know that users might not want to improve their behavior. So this should be used as as input when you design your system. Maybe instead of trying to change the user, you will try to give incentives for them to make conscious decisions. So you should aim at conscious choices and not behavioral change per se. Again, as I said yesterday, the algorithms are not enough. Also, the visualization by itself is not enough, but if you mix them and if you consider individual differences, you find very interesting effects. So you have to consider what is the social context of users, and in this case was if they had political content or not. Of course, we don't know why this happens, so as future work, we propose to run a qualitative study using the same setting. In the URL on the slide, you will find all the code used to implement this system, the Twitter cloner, the recommendation algorithms, the visualization. So I encourage you to replicate this experiment. Thank you, and I will gladly answer any questions.
Thank you very much. Michelle is coming to the microphone.
It's very interesting work. I'm just wondering, because in your hypothesis, it seems you use the Twitter as information, a user, and you're trying to actually to create your data portrait, right?
Yes.
You can hear me, right? So I'm just wondering, now you did this one, and do you really know, because when a user is interested in something, doesn't mean this person is agreed to something, right? So in your study, has shown that because of a diversity of the, let's say, the topics, this person actually has changed his or her view in some way.
Thank you for the question. We are not trying to change the political view of users, if that's what.
Right, I'm saying, has this kind of a different diverse opinions in some way has any influence on the user?
Actually, we don't know yet. That's why we want to run a qualitative study.
Okay, so this study hasn't shown that yet.
Exactly. So we know that they did something different because they spent more time on the application when the conditions were met, but we don't know why.
Okay.
So we
and you didn't have a question, a survey to ask them what they think, what have they thought, right?
No, because they connected their accounts and they just visited the site. There wasn't any form on the site.
Yeah, I was also wondering how this connects actually to your motivation, where you said that you want to bring together people that have diverse opinion, because in fact what you did in the study, if I got it correctly, is only basically topic similarity. So you did no sentiment analysis.
Exactly.
No.
Exactly. So the idea is that previously we analyzed if intermediary topics gather people from diverse political views on hashtags, on keywords, and they do. But we still do not know how much diverse they are. We know that they are diverse in a specific context, in Chile at least. So that's why we perform this only for Chilean users.
Okay, got it. Are there further questions? If not, then let's thank Eduardo again. Thanks a lot.
Thank you very much.
We come to the next presentation. Another long paper. And this is also something that we've seen yesterday in the demo session, or in the posted demo session. This is Chord Ripple, recommending chords to help novice composers to go beyond the ordinary. And the presentation will be given by Shengxi. And it's interesting to see who is the composer in the audience? Let's see. So, Jim, another 1, 2, 3. So pay attention, I would say. Yeah. So you learn how to go beyond the ordinary, which is the goal of every composer, I guess. Otherwise, you wouldn't do it. Okay, thank you.
Thank you. I'm going to plug in the sound. Sometimes you might hear some loud. Okay. Thank you very much for the introduction and for helping me motivate the work. We want to make it easier for novice composers to explore different alternatives so that they can go beyond the common chord progressions and be a little more adventurous. So first, I'm going to start by trying to give us a 2-minute crash course on chord progressions, a very high level. So here you see the first verse from Love Is All You Need by Beatles. You see there's repetition. For example, the first 3 lines starts, there's nothing you can, there's nothing you can, nothing you can. And the chord progressions also reflect this kind of repetition. If you're not as familiar with the chord progressions, you can just read the red symbols as alphabets. So here we have the alphabets going down, G, F sharp, E. And also in the music, you'll hear the bass line going down. And you see that pattern being established and repeated. And when you get to the 3rd line, you see this variation, kind of a departure. And the difference here is it started the phrase in a chord that's 1 step higher than before. And every time I listen to this, I feel something pulling me up, and my neck stretches a little bit. So let's see if you would share that sensation too. So you can see how it deviates from the pattern is that it's actually generalizing from the logic that it's established. So the logic we have here is a very stepwise motion kind of going down. And here we start a little earlier, a little higher, and then we keep going down. And actually the next phrase is also a continuation of this. So you see A, G, F sharp, E, D, C, B. So let's hear this.
There's nothing you can do that can't be done. Nothing you can sing that can't be sung. Nothing you can say, but you can learn how to play the game. It's easy.
Okay, it's easy, but what do student composers find hard in this? So we interviewed a bunch of freshmen and sophomores in music composition, and we realized it's not necessarily the hardest to come up with an idea, but once you have an idea, which takes the form of a sentence of a chord progression, they don't know how to develop it. They don't know kind of the techniques for variation, what are the generative rules they can use. And of course, there are students who find it difficult to break out of the common chord progressions and to find more original ideas. So what do students do when they get stuck? A lot of them have these 3 strategies. They improvise on an instrument, and by chance they could land on some new chord, or they use music theory to find out what are the alternatives they have. And a lot of times we listen to other songs to find inspiration. But it's hard to relate the other songs to what we're actually doing. And to find that analogy of how do I do that in my thing. But with machine learning, we have an opportunity because It can go through hundreds and hundreds of songs and synthesize what are the patterns, what are the common things that people do, and recommend that to you in a way that relates to what you're trying to do. So we're building this creativity support tool, and we want to make it easier for novices to explore these more interesting and relevant variations. So two of the goals is we want to be able to give you something that fits with your original intent and that is appropriate for the current context. And we want it to be more novel in the genre. So music is a very sequential process, so there's a lot of temporal constraints. So we tend to think about we want things to smoothly transition. So when we do recommendations, a lot of times we focus more on the context. And given this context, we're trying to recommend what fits in the best. But here, we want to focus more on what is similar to what you're trying to do so that we can actually preserve your intent. So one of the things when you try to recommend according to the context and what's the most typical in the context is that we faced the challenge of music being this long tail distribution. So a lot of chords happen, so some chords happen many times, but a lot of the other chords only happen a countable number of times. And we also have this sparsity challenge. So if you look at a transition matrix, a lot of the cells are black. There's no counts there. And here you see two more bright columns. You see some yellow and orange. Those are the 5 chord and the 1 chord. You can think of it as the C and a G. And those are the most popular chords that a chord would transition to. So if you recommend according to that to fill in the blanks, then what you get is kind of this monotonous set of chords like C, F, and G. And that's not as exciting if we're trying to build a creativity support tool. So we want to kind of use what you have already to anchor the recommendation. So we want to find chords that are similar to what you're doing instead of just filling in the blank with what's the most typical. So this empirically would give you a more varied set of chords and also things that are more adventurous in the current context. So how do we model similarity between chords? There's existing models in music theory that thinks about if chords share a lot of the same notes, then they're considered similar. Or if the chords are very dissonant with respect to each other, then they're dissimilar. There's also work in psychology that thinks about if we let a listener listen to a sequence of chords and then give you another chord and say, how stable does it fit into this context? And that helps define the similarity. But for composing, we want something that's based on how chords are actually used in songs. So we go to our friend language. Music and language always has a lot of parallels. And in language modeling, there is this notion of similarity. That is, if words are used in similar contexts, then we're going to consider they're similar. Oops. I think somebody wants me to connect to the internet. And I can't see my mouse, so I'm trying to improvise, and by chance, I'll land on connect. Okay, let's see. Sorry for the interlude. Okay, so I gave it away. The model that we're using is word-to-vec, and it addresses the challenges of words being these discrete tokens. They don't relate to each other in trivial ways. So the way to kind of have them share some semantic structure is the model works by first projecting these discrete tokens into a continuous latent space, and then each word becomes this dense vector, and this vector is used to predict the context. So if words are surrounded by very similar contexts, two words being used in very similar ways, then they should have a vector that's really similar in the space so that they can have this kind of smooth function that's doing the prediction. And here we see kind of a 2D projection of some of these embedding spaces that come out of the learning. we see countries, and we see capitals, and we see them related in a way that everybody has that same direction, that same vector pointing from countries to capitals. And this allows us to do interesting analogies, such as if you take the vector of France, minus it by the vector of Paris, and then plus Germany, then you'll get Berlin. So we see kind of this vector algebra helping us to get at a lot of the semantics. But how would this look like in music? So there's a lot of similarities and differences among music and language. So they share a lot of the common characteristics. Every culture has some form of language, has some form of music, and it induces very strong expectations when we listen to them. We can kind of guess what might come next, and if that expectation is violated, then we get surprised. So it's richly structured, but music is also unique in many ways. There's less separation in syntax and semantics. And it's modulo 12. It kind of goes back to itself. So if you go up the piano, so say here you're just thinking about the white keys, then it's kind of like modulo 8. But C, D, E, F, G, A, B, C, then you land back to where you started. And also it has this cyclical property. So in music theory, we talk a lot about the circle of fifths. And these are the scales arranged in a way where if you're close in the circle, that means you share most of the common notes. So what do we see when we learn from 200 rock songs? So this is the embedding, and I've highlighted all the major chords and the minor chords here. And so each chord is represented as a vector in this space. For example, we see C major here, and this is a low-dimensional projection of the original space. And the way to find what chords are similar is to look in the neighborhood. For example, we see A minor here, which is the relative minor of C major. So that's a good sign. Like we see things that we think are close to be close in this space. And if we go on and connect all the major chords, what we see is a circle. We see this emerging from the data, more or less. There's definitely, so part of the artifact is some keys, there's more songs in some keys and less songs in other keys. So what happens if we connect all the minor chords? And voila, yes, you get circles again. So there's a lot of structure, and this gives us confidence that the model is capturing something that's musical, and that we can use it to help recommend chords to composers. So now we have a way to think about similarity between chords. But similar means that statistically, they happen in very similar kinds of contexts. But for this particular context, it might not fit as well. So if a composer wanted to use this recommendation, she might have to fix what's around that chord to make the transition more smooth. So we propose the idea of reworking the context, which is the ripple idea. If you change one thing, you kind of have to change what's around it, so you ripple out. So here is how that would look like. But of course, this context, you might want it to be closer to what you had before. And so we have these additional constraints thinking about also the similarity between context. So here we're kind of combining the previous approach of thinking a lot about context, being smooth, but also thinking about similarity so you can preserve the user's original intent. And it wants me to be connected again. Let's see. It's like a timer. So here you can imagine we can do some kind of trade-off between these two objectives. You can want something that's more typical in the language and sacrifice how close you are to the original. So in some ways, you're kind of using the similar chord as a guide to explore in some other space in the data. Or you can want something that's closer to what you had before. So we kind of built this into Chord Ripple, a tool, and we want to know, is it able to help novice composers come up with more novel chord progressions? That's kind of the goal of a creativity support tool. And we also want to know if they're happy, if they're satisfied with what they came up with. So these are two of our measures. And novelty is considered to be if you're writing in a particular idiom, say you're trying to write a rock song, then if what you're doing is less typical but still appropriate, then it's more novel. So we did a control study on these three types of recommendations that we talked about earlier. And the task was to transform a common chord progression. And the three conditions being the typical, the similarity recommendation, and when ripples are added. So when we first started, we didn't know how people would react to ripples, because ripples is changing many things at once, and people might not be able to relate to it as well. So this was a within subject study. Everybody attempted all the conditions. So I'm going to give you a quick demo to see how this tool works. So this is a chord progression they start with. And here you have the toggle for the three different kinds of recommendation types. And say I'm starting with the typical kind, and I want to change the second chord to see what other variations I can consider. So these are some of the chords. And I'm going to listen and compare and contrast. I want to hear how it fits into the current context. I listen to something else. Yeah, and I quite like that darker sound, so I'm actually going to use it. So that replaces what I had before. And I'm going to explore the next chord. But the typical recommendations don't give me a lot of interesting options. So here I want to see what similar recommendations would give me. And it gives me a much different kind of distribution, some like 7th, 9th chords, some inversions. Again, I explore and listen. Oh, I really like that sound. But it doesn't fit into the context as well. So now I'm going to use the ripples to help me kind of do the work. Yeah, that transitions a lot more smoothly. And I decide to use it. And this is what we end up with. And then we can save it. And here is the user can give a rating. This is the self-assessment that we use to gauge like how people are satisfied or not with what they came up with. So that was a quick demo. And the results from the study, we found that students were equally satisfied with what they came up with across the different conditions. The average rating was a 4 out of 5. But in the similarity in the ripple condition, students were able to generate more novel chord progressions. And they used ripples a quarter of the time. And some of the feedback that they give about ripples is that ripples were able to provide context for the chords. It provided guidance, it made it less burdensome on it to make a choice, to make a change, and it also gave them new ideas. We also wanted to know more, kind of a more intimate view of how did students interact with chord ripple. So we did a structured observation, which was a more musically natural thing. So we asked students to bring in their own chord progressions that they're working on for a particular piece. So here the students are more intrinsically motivated. And I give you a quick example of one of the participants. So he came in, he had this self-perception of, oh, I'm bad at breaking out. So I'm actually going to write a minimalistic piece where things repeat. But by interacting with chord ripple, he realized he was able to find variations. He composed a second phrase, a third phrase, and he decided, no, it's not going to be so minimalistic. I'm actually going to invent a larger piece with a richer chord progression. Okay, so that's and thank you very much.
Thank you very much. We have time for questions. Yes?
Yeah, one question about the, you showed the chords for the 200 songs
Mm.
and you showed them in their original keys. Did you normalize those to same key and relative minor?
Yes, so actually for the tool, we normalized everything to C. Yeah, and we told the participants that we're composing in C for the task. Yeah.
Further questions?
Hi, very interesting
Thank you.
application of recommender system. Great talk. So I just have this question. You said in the RIPPLE condition, you have two things you're trying to balance. One is the similarity, another is the how smooth the transition is. So I wonder, in your design, have you explored giving user the control of how do they want to make the trade-off?
Yeah, totally. That's kind of the next step that we're hoping is to allow users more control, maybe more transparency, and yeah, seeing how different students might come up with different configurations and how that actually reflects maybe how adventurous they want to do, or actually can reflect the stage they are in the compositional process, because you have this divergent stage and convergent stage. So in different stages, you might want to explore a different range of things.
So are in the current design, are those chords sorted in any order, or they are?
Yeah, they're sorted in kind of typical to novel. So how often the chords actually appear in the rock songs.
Thank you.
Thank you.
I was wondering, currently in the RIPPLE condition, you basically have this kind of context of 3 chords. Yeah. So I was wondering, why 3 chords? Yeah. And to which extent you can enlarge this,
Yeah, I think that would be a nice control for the user to have already. What we realize is actually chord progressions a lot of times are not very long. They can range from 6 to 8. So changing 3 things is actually a lot. So we were worried in the beginning that people won't use ripples because it changes too much of what they had before.
And this is exactly, I think, another interesting question, to which extent, users felt that this was still their own composition, because I imagine if you extend actually the chord ripples to the whole sequence, they would not think that they've composed it. So
yeah, it's very subtle. So it also has to do with music kind of semantics and structure, because in a way it's trying to preserve your high level intent. It's trying to preserve the function of how you laid out the skeleton, but the actual rendition is different.
Yeah. Okay. Any further question? No? Then thanks again. Yeah,
Thank you.
Okay, and now we come to the first shot paper presentation. It's about learning item temporal dynamics for predicting buying sessions. And presentation will be given by Ossi from Haifa University. I guess it's Haifa? Yeah, you're Haifa University, correct. And VGA, or
The other one.
the other one, HDMI, is this possible? Or VGA, only VGA. There must be another adapter, actually. Wait,
Here it is.
there is an, exactly, just take that
I
cable.
didn't agree with what you asked her, because I think that when people choose, that's
Yeah.
their choice, so that's their own.
Yeah, yeah,
So
okay,
it's just
good.
like playing
Yeah,
guitar.
yeah,
Thank
okay.
Anyways,
Please.
yeah, sure. Just a second. It worked in the beginning. Can I just take it off for a second and then we'll try again? It should be okay. It's for me. It just. It feels like it recognizes it.
Yeah, wait. No, no.
I don't know, yeah.
We want to use this one. You want to use this one?
But this didn't work.
You sure?
It didn't work before. Just the other one worked.
So
Okay.
this looks very good.
So I'll just hold it. or-
Yeah, let's see. Wait.
Okay. Thank you.
Okay, please.
Okay. I'm Osi Mokrin from Haifa University, and this is a work that was done by Tzvi's and my student Veronica, who's not here, but Tzvi's here, and he's also in the work. And learning item temporal dynamics for predicting buying sessions. Quite a contrast from. Okay. Sorry?
Buying Beatles songs. No go ahead.
Yes, yes, well, no. We quite changed the scene now, and instead of composing music, we're on an e-commerce site, and we have random users coming in and starting to click on items, and we would really like to know whether they're going to end up the session in a purchase or not. The problem is that these are random users and we know nothing on them. We have no personal information, no history. They're just coming in, they click on items, and we would like to know whether they're going to purchase, because if they're not, then we might introduce some recommending algorithms and sort of push them towards the purchasing part of at the end of the session. But having no no personal information means that we can only resort to item information. And we have the clicks on the items and the time it was taken. So what was interesting for us to understand is whether there are characteristics of the items, temporal characteristics of the items that we can actually exploit in order to understand whether the session is going to end up in a purchase. And more precisely, we were wondering whether there are trending items currently and whether the presence of trending items is an indication for the outcome of the session. So this was what we were looking for. This was our research question. Our primary data set was the YouChoose Rexis Challenge data set that was published a year ago. And it's a large-scale data set with clicks and buy events for over 6 months. And I'm sorry, did something. That shouldn't happen, I'm sorry about that. So it should be playing. I don't know why it's not playing. It shows me that it is playing, you see?
Wait.
Let's do it again. Something.
Let's swap this place.
Okay.
Oh, no?
Oh,
Is it right? No,
Right.
okay, wait.
No, we changed something.
Wait. We need to swap this place again.
We swapped, yeah. Can we swap again?
See, should work somehow.
No, we need to swap again.
Where's the thing? Where's the, wait. To that side? There it is.
Sorry about that. So we had a data set with the session information of what items were clicked and at what time, and we had another file with the outcome of the sessions, whether they ended up in a purchase or not. And as you can see from the data, 95% of the sessions ended up in not purchasing anything, and only 5% of the sessions ended up in a purchase. And there was a lot of missing information on the items. We didn't have the category or the price for the majority of the items. So we decided to rely only on available information, which is the click and temporal dynamics and information on the items. And if we look at this sessions length, we can see that there is a long tail distribution, but I want to go further into the differences between purchasing sessions and not purchasing sessions. And on the left, you see non-purchasing sessions, and over almost 40% of the sessions were only 2 clicks long. While on the other side, on the right side, you see purchasing sessions, and you see that actually there are, the distribution is more even, and there's almost 20% of the sessions that were 10 clicks long and even longer. So that was a good indication. And we designed a model where we had that data set, and we had a trending modeling session for 80% of the data, which we took, and I will explain in shortly. And then we collected all the temporal characteristics of the sessions and balanced the data and put it into a classifier, really. Okay, so the trends modeling is the following. If we look at a table, what we did is we looked for recent trending characteristics of the item. So if you look at the last of the 3 days, 91, 92, and 93, and we have 3 items. So the first item is trending, is positively trending. It participated in 6, 8, and 9 purchasing sessions, while the item number 2 is a stable item, and item number 3 is actually has a decreasing. So for us, an item, if an item was clicked on in a non-decreasing number of buying sessions, we term it either a trending or a session product, then it is included in the session presentation phase. If not, it is ignored. And the way we model the trendiness of a session is the following. First, we model the trendiness of the item as the ratio between the number of buying sessions that it participated in a time window, normalized by the total number of sessions it appeared in. And then a session is as trending as its maximal trending item that appeared in it. And we have number of clicks in the session and temporal aspects. We have imbalanced data, so we use the smart to balance it, and we use 3 classifiers, and we vary the experiments for different time windows, and we did feature selection. We found that trendiness and session length are important, so we did the experiments with and without these parameters. And we also had another, which I don't think I will have time to explain. So if we look at the results here, what we see that we are able to identify quite well sessions that will end up in a purchase. And actually, if we vary, and what you see on the x-axis is the days that the time window that were taken, and for each day period, for like 2 days and 3 days, up until 6 days, we examine with all the features or without the trendiness of items. And you can see that we do much better when we take into account the trendiness of the item. We also did another experiment in which we used some sort of a smoothing function of the trendiness of the item, not specific time windows, but actually a more relaxed aggregation of the trendiness, and that really even performed even better. And this is I mean, you can go, I don't have much time, so you can go to the paper for the details. Since we submitted, we were able to obtain another data set which was much larger from Zalando. And you can see that it's a much larger data set, and the results are even more distinct and even better on this data set. So if I'll go to the conclusions, what we see is we have novel method that uses temporal dynamics of the items, which we term trendiness, together with temporal features of the session to perform a session-based buying prediction, whether the session ends up in a purchase or not. NB tree and bagging outperformed logistic regression in prediction measures for all days and for all presented methods. And we have some limitations where the future directions are how the above results will change along the session, because if we'll go from the first and second click and we'll be able to predict as early as the first clicks, this would be a much stronger result. And we would like to set the result the number of cases participating in trending analysis. Okay.
So maybe while we take a quick question, the next speaker can already set up. No? Be nice. Yeah, Khalil. So questions? If not, I'll start with a quick question. So I was wondering how important the influence of the item, of the characteristics of the items themselves are. So there are items that turn quickly, you know, where there are thousands sold on a day. Others are much slower in terms of volume and so on.
This is why we normalized everything with the overall number of sessions that they participated in.
And what type of, the first corpus, the second one, I guess, was shoes and things like this, you know, if you said Zalando.
Yeah,
and
Zalando,
the first
right?
one?
It's products from you choose. It's a variety of products from TVs to, I think, even sugar.
Okay.
Yeah,
Those are all
okay.
type of products. Okay, no further questions? Okay, thanks again. Yeah. And we come to the second short paper presentation of this session that's entitled A Live User Study of Opinionated Explanations for Recommender Systems. And a presentation will be given by Khalil.
Okay. Good afternoon. My name is Khalil Mohammed, and I'm a PhD student from. I'm a PhD student from UCD, and I'm part of the Insight Center for Data Analytics. This afternoon, quickly, I'll just brief you on a subset of ongoing work which we've been doing in the area of recommender systems and explanations. But what makes this work unique and different is that we are using user-generated reviews to generate, we're using user-generated reviews, So we are using user-generated reviews as a source of recommendation knowledge and explanation knowledge, which is different from other approaches that is very conventional. So I'll quickly describe the result of the user study which we've done, which is basic and simple, that checks the type of different explanation interfaces we create using our methods. So these days in recommender system, it is not just enough for you to present a list of recommended items. It is almost mandatory for you to provide some sort of information that tells the users why or how those recommendations were made. And if you do this and you do it very well enough, then you might be able to persuade the users to do or act on those recommendations which you provide. So the motivation for this work is that we've been trying to produce recommendations and explanations basically from user-generated reviews. And as we all know, these user-generated reviews are normally unstructured. So what we do generally is we pass these reviews through an opinion mining process to generate a semi-structured set of item descriptions, and then with that, they form the basic information structure for the recommender system and the explanation engine. So I want to tell you about the explanations that we are producing. And everything I talk about henceforth is going to be in the context of TripAdvisor, because that's the main data set we've used for this evaluation. Notwithstanding, the methods I will describe can be used on any other data set you have, as long as it has reviews, users, and items. So here is the type of explanations we generate. And as you can see in the background, there is a hotel, Clontarf Castle, which is a popular hotel in Dublin, and the type of explanations we generate as such. So this is the explanation. And our explanations contain a number of components. We normally separate the pros from the cons. So what you see at the top there are the pros, and at the bottom are the cons. And the features are actually directly mined from user-generated reviews. So bar, lounge, free parking, and restaurants are pro features, and they've been mined from user-generated reviews. And people that have written about this for this particular hotel have given bar, lounge a very positive review, free parking, and restaurants. Likewise, if you look at the bottommost part of the explanation, which is the cons part, there's airport transportation and leisure center, which have also been negatively reviewed. And one other thing to notice is that we also compare each of these features to other recommendation alternatives. So you can imagine this particular item being recommended in a set where you have more than one item. And this explanation tells you whether this particular item is better than or worse than the alternatives. Hopefully, this will help in making decisions. So we've described in the paper in detail how we generate these explanations. And because of time constraints, I wouldn't be able to explain it fully. However, at a very high level, what we do is we start with any given hotel in a set of recommendations, and then we split the features into pros and cons. We apply some filtering and some ranking, and then we determine whether it is better or worse than majority of the alternatives, and then we're able to target as a compelling or otherwise. So whatever appears in an explanation must have gone through this very big process. So the purpose of this paper is that we wanted to know how people will react to these explanations. We wanted to know if the explanations were easy to understand and if they were helpful. So we recruited 181 participants, mostly postgraduate students and researchers from our research center. And we prepared 9 different interfaces, 9 different explanation interfaces. And what we wanted to see was whether the separation into pros and cons had any value to them, whether the sentiment bars, which are those colorful green and red things, had any value to them, whether comparing the recommended item to alternatives, which is a reference set, had any value to the users, and whether displaying precise percentages, which are numbers in explanations, had any value to them. And in this case, when I say value, I mean clarity and helpfulness, and utility. So this is an example of one of the explanation interfaces. This is just a mock-up, so the first one is a better one. But this one shows pros and cons with the sentiment values, green and red. There's another example of it. This one has pros and cons, and it also compares the recommended items to alternatives, and it also shows percentages, which is a more complicated variation to the previous one. But I won't have time to show all the 9 interfaces, so what I've done is I've gotten fragments, and I've listed them from A to I in there. But the details are very clearly described in the paper. So after recruiting the participants, what we did was we described a booking scenario for them, and each participant was asked to rate each of the 9 interfaces on a scale of 1 to 10, 1 being helpful, and 1 being not helpful, and 10 being very helpful. And they were asked to rate it for clarity and utility. So the presentation order was shuffled so that we reduced the likelihood of having an ordering effect. And after reviewing all the 9 interfaces, we asked them to rate the usefulness of the different explanation components. Now those components are the pros, cons, the sentiment bars, like I've mentioned earlier. So quite quickly, this is the result for the clarity and utility of the explanation interfaces. Notice as we go from left to right, what we have on the x-axis are actually the explanation interfaces, and the right is the response rate we got, positive response rate. So as we go from left to right, you notice that complexity reduces. So the first one has percentages and the sentiment bar and the pros and cons, and the last one is just the sentiment bar. So this is quite interesting in the sense that although complexity reduces, it can be explained that since the domain is something that people will be spending money, so if I'm booking a hotel for $500, it is something that I'll probably need to know a lot of things about before I do it, as opposed to going down. But this is the result we got in there. And what we found is that all the responses were above 50%. So essentially, all these interfaces are good. Now, this is a very basic, like I said, evaluation and preliminary evaluation. So I will discuss more about it, hopefully, in the future. And for the components in the explanations, we have the pros and cons, the sentiment bars on the x-axis, and this is the positive ratings we've gotten for them. They are also quite high, but there's also a trend. So essentially, as the complexity of the components, so as we move from left to right, you see they become less complex. Sorry, it's supposed to be more complex. So pros and cons are the most easiest ones, and percentages are very detailed and requires people to think. So what we've found is that users actually expressed a preference for interfaces that combined a number of different explanation components. So the simpler ones don't actually give the best results. However, the simpler components are what the users prefer. This is a very basic test. This is part of an actual ongoing process, which is an explanation system that is used for ranking recommendation. So we will do more tests to test the significance of what we have, and hopefully more experiments with users. Thank you very much.
So quick question, Zvika?
Zvika from the University of Haifa. I've got a question regarding the initial part. Maybe it's a bit off to your study. You are creating the explanation based on feature extracted from user reviews.
Yes.
The features that you are extracting are a specific set, a finite set of features, or you're building the set of features based on the content?
So
what kind of features you are extracting and how do you do that?
So we've described this in detail in previous papers, but we're extracting from the content entirely. So we're not looking for specific features. So what we do essentially is we dig through, and it's quite an elaborate opinion mining process, and we extract all the features. And then we do a little grouping of these features into subcategories, which has also been described in, I've taken out the slide, but the paper is at the bottom there, which is very initial in this particular work. And with that, we're able, that summarization process, we're able to prioritize what shows up in the explanations.
Thank you.
Yeah.
Okay, Khalil, thanks again. Yeah. And we come to the final presentation of this session, which is a TIIS paper presentation on I would say, a historic landmark data set, the movie lens data set, and Max is giving the presentation. Please.
Hi, my name is Max. I'm a research scientist with Group Lens at the University of Minnesota. And as part of my job, I'm the caretaker of a system called Movie Lens and the resulting data sets. And that's what I'm here to talk to you about today. And we wrote this paper for TIIS. And in case you haven't figured this out, there's actually a way to look at all of the TIIS papers if you go to the TIIS website /IUI16. So you can check out all of the different papers right there, I guess just for the length of this conference. So Movie Lens is a website that lets users rate movies, and they rate movies because they want to get personalized recommendations in return and predicted ratings. And because people like to do this activity, we've collected a lot of ratings over the years. Movie Lens first launched way back in 1997. And we've collected the result of these ratings into a series of data sets that we've made publicly available as a resource for people who want to explore ratings data. And fundamentally, I think that the Movie Lens data sets have been prominent because ratings data and these types of interfaces in general have become so pervasive in the systems that we use on a daily basis. And as a result, we have some measurable impact of the data sets that's kind of interesting. So the data sets get downloaded hundreds of thousands of times each year, and they've been cited by thousands of academic research papers and by books as well. But it's not just research impact. The MovieLens data sets have a variety of uses. So technical uses. If you're putting together a programming book or a blog on some technical concept, you might want to talk about movies and use that as an example for coding up your, for communicating what you want to teach. Educational purpose, computer science curriculum, for example. We have a Coursera MOOC on Recommender systems that uses the MovieLens data, as well as industrial purposes. And so what I'd like to talk to you about today is two things. So first, I'd just like to tell you what the MovieLens data sets are and which ones are available so that everyone knows about them. And then the second thing is I'd like to quickly discuss some tension that we've observed between our desire for sort of a pure data set that reflects some truth in how users interact with items and the desire for systems to change over time. So let's start with the data set. So fundamentally, the MovieLens data sets describe user movie rating behavior as a long list of tuples like these, user movie rating timestamp. For example, one row might say that Max rated Toy Story 4 stars at a particular time. Rating values represent half-star ratings from 0.5 to 5 stars, so 10 discrete values, and the timestamps represent the most recent rating event. We've released 4 benchmark data sets that are designed for researchers primarily. They're designed for replicability, really. These are stable data sets. They don't change. We've released one about every 5 years. The most recent one we released last year. And one way in which they've changed substantially beyond just their size is the more recent data sets have many more movies in them. And so the sparsity of the data set has grown substantially. So because there aren't very many users who've rated all 27,000 movies, right? So that's something to consider. But for researchers who are planning new projects, we recommend using the 20 million data set. But if you wish to replicate prior work, then that's the best use for the older data sets. And more recently, we've released a new set of data sets called MovieLens Latest. And a lot of people have expressed the desire to look at new movies because we care more about the things that we saw last week and not things from a 1998 data set. And so we regenerate these periodically. And so these are really designed for non-research uses, for educational or programming tasks. And the small version of the latest data set is designed for cases where you don't really want completeness. What you want is something that can be used for instructional purposes. So that, you know, students in a computer science class don't need a 20 million record data set. They just need something small that they can quickly operate on and download. Okay, so let's shift focus. You all know what the data sets are. Let's talk about some things that maybe you haven't thought about when you've done your own data set-based research. And what we've learned in MovieLens is that there's this interesting tension between what we want as system builders and what we want as the maintainers of a data set. Because our system wants to change. So since 1997, there's just been a lot of pressure. Technology has changed in a lot of fundamental ways. And we want to stay current, we want to fix bugs and introduce new features. In addition, we run A/B tests, we try beta features, etc. All of the things that all systems do if they hope to stay fresh and current. And not only this, but the context of use of a system changes. Netflix wasn't around in 1997, and now they're just a very important part of our competitive landscape. Not to mention the shift from Netscape Navigator 4 to a modern Chrome browser or an iPhone. And so we can look back kind of at a superficial level to see some of the changes that have happened to MovieLens over the years. So this is the first version from '97. And here's another version from 1999, from 2000, 2003, and our most recent version from 2014. But those are just superficial changes. Yeah, the site looks different, but at its heart, we've actually introduced a number of very fundamental differences. So the core flow of the system, how do people find movies? How do they browse and search through the system? The ratings widget itself, so the core mechanism that the MovieLens datasets are derived from has changed. In 2003, the #1 feature request in MovieLens was to add a half-star ratings widget. And so we did that, so it went from 5 discrete values to 10. And in 2014, we changed it to a clickable star widget, which everyone's used to these days. We changed the core recommender algorithm. We changed the new user experience and what we require when people sign up. We've added tagging features, movie management features, social features, and many other things. Plus, we've run a bunch of experiments there. So we're an active research lab, and we've treated MovieLens as a test bed for learning about the world and online systems. And all of these things have impacted how users interact with the system, and therefore the kinds of data that they generate and put into the data set. So the good news, if you use the MovieLens data set, when I generated this chart, it gave me hope for the consistency, because I've given you all these reasons why you shouldn't believe that it's consistent. But if you aggregate user rating behavior by month since 1997, it's remarkable the consistency that you observe. So the solid line that runs through this chart represents average rating by month, and it's held steady at right around 3.5. The gray area is standard deviation. So 3.5 stars plus or minus 1 star is where users apparently, that's how they rate things. And despite all our best efforts to change that, it hasn't changed. And so that's kind of remarkable. The dashed vertical lines represent the change to the half-star ratings widget and the change to the clickable star rating. So this is a very short talk for a longer paper. Some things, if you're interested in following up and looking at the paper, if you're interested in the story of MovieLens, it's kind of a fun success story from the research world, I think. And so we share lessons from running a real system in a research lab, and there are lots of fun charts and descriptive statistics. The other thing that's in the paper that you may or may not be interested in is a set of best practices for people who hope to do ratings-based data set research. We discuss some alternative data sets as well as best practices for using our data set. And I'd like to quickly say thank you to a large number of people who deeply committed to this project over the years. So thank you to all these people and MovieLens users. And I'd be happy to take questions. Thank you.
Do we have questions? Aaron?
Aaron Quigley from the University of St Andrews. So I was wondering, given all the data you have available and what you can see everyone else doing in terms of the research field, are there directions that you think others should start looking towards, other big open territories for this type of, improving this data? And are there also uses that you think you would like people to stop using the data for, both of those directions?
Oh yeah, that's actually a great question. So something that I find very interesting, so I went to the Recommender Systems conference this year, and I'm observing this great tension in that research community because of a belief that data set research is just inherent with many limitations. And so we saw in the opening keynote that he had RMSE with a big circle and a line through it that said, don't do it. And data set research often encourages that kind of sort of shallow interpretation. So that's one thing, so that's the warning, is a lot of the community is starting to shy away from the use of data sets like MovieLens. That being said, about 1 out of every 3 papers referenced the MovieLens data set at that conference. So that's another tension that I observe. In terms of opportunities for data sets, one thing, a trend that I see is that ratings-based systems are falling out of favor. And what's coming into favor are implicit feedback systems. So you'll see in Netflix, for example, the star ratings widget has become much diminished in its user interface importance. And what recommender systems are often built around now is observing user behavior. And I think data sets that can capture that level of detail, including dwell time, so what people do and when and how long they use the features, I think that sort of data set would make people pretty excited, and that would get a lot of traction.
Thank you very much. I'd encourage you to do a Kickstarter so you can make a movie of MovieLens.
Oh, great.
Okay, so Max, thanks a lot again.
Thank you.
And let's thank all speakers of this session, because we are at the end. And now we have a coffee break until 4 o'clock.